This is our fifth online video tutorial, and our today's topic is linear mapping or linear transformation. What is a linear mapping or what is a linear transformation? For this, in this definition, we will be involving the terms vector spaces, because we define actually linear transformation is a kind of mapping that maps from one vector space to another space. That is why you should recall the definition of vector spaces. Now you know very well that what is a vector space is. Vector space is such a set which has special properties, and it should have a field of scalars which may be the set of real numbers or the set of complex numbers. So suppose we have a field K. For example, we have a field K and we have two vector spaces V. This is a vector space over the field K, and we also have another vector space U that is also a vector space over the field K. It means that both spaces are vector spaces over the same field K. And now we define a mapping F from V to U. That is, I'm sorry for the thunder sound. So there is a mapping from V to U, and if this mapping, we define a mapping F like this, and for the sake of you should not be confused, you should not mix this F with this one. Therefore I should remove this F. We have a field K, okay, and the capital F below over here, this one, this is actually a mapping from V to U. Now if this mapping from this vector space to this vector space satisfies two conditions, then we say that this is a linear mapping or a linear transformation. And what are those two properties? The first property is, for example, I take two elements small u and small v from the set of domain in V of K, okay, and I check if this property is satisfied, that f of u plus v, this is equal to f of u plus f of v. If this property is satisfied, and there is another property that says, for example, I have a scalar value alpha from the field K, and if the function satisfies f of alpha into u, where u is the element of the capital V, and this is equal to alpha into f of u. If these two properties are satisfied for the elements uv in the vector space V and alpha in the set of scalars K, these two properties are satisfied by the mapping defined like this, then we say that such a mapping is called a linear transformation. So this is how we define the linear transformation, and there are specific properties of the mapping linear transformation F, and that property is, for example, if you look into the second property, then you will see that if we put alpha equals 0, for example like this, if I put alpha equals 0, then it will become 0 dot u, which we can say that this is equal to f of 0. Then this f of 0 u, according to the second property of the linear transformation, this is equal to 0 into f of u. Now it does not matter whatever is the value of f of u, but because of this 0, the whole value will become 0. So I can see that f of 0 is mapped on what? 0. So we can say that f of 0 is always 0 whenever f is a linear transformation. This is the first property of the linear transformation. It maps the vector 0. What is this u actually? This is a vector. What are all the values on which f is operating? These values are actually the vectors from the vector spaces. So if is when operated on the zero vector, it will give you the result as a zero vector also again, because the range is also a set of vectors. Therefore we say that if when operated on the zero vector, the result will be a zero vector. This is the property of linear transformation. Another property is that if linear transformation is such a mapping which preserves the two properties of the vector spaces, that are the addition and the scalar multiplication. For example, you have seen in this definition over here, the first property is actually what? This is the property of addition is preserved, okay, and similarly we can see that the property of scalar multiplication is preserved. So these are some properties of the linear transformations. Note that there is another property. For example, if I combine the property 1 and property 2 in a single property, and I will take two constants a, b from the set of scalars, and if I say I take uv two vectors from the vector space V, and I write f of au plus bv, then by the two properties collectively applying the first property, it becomes like this. And according to the second property, it becomes, I'm sorry for the writing, you understand what I mean. So when both the properties are applied, so the whole definition of two conditions has merged into a single condition, and sometimes authors define linear transformation like this: a linear transformation if is a mapping which satisfies this single condition. So this is how we can redefine the linear transformation. And more generally, if we generalize this definition, okay, let's come to the formal definition, then I will explain this. This is the definition of linear transformation, which I explained. We have two vector spaces V and U, and a field of scalar. Both the vector spaces are spaces over the field K, and we define a mapping from V to U such that it satisfies these two conditions. One is the preservation of addition, and other preserves the scalar multiplication property. When these two properties are satisfied by this mapping, we say that this mapping is called the linear transformation. And it is observed that this linear transformation preserves this property of addition, which is the basic properties of vector spaces, and similarly of that the scalar multiplication. And we note that I explained earlier that if I put 0 is equal to here is equal to k over here, then I get f of 0 is equal to 0. It means that in every linear mapping or in every linear transformation, linear mapping and linear transformation means the same thing here. Then for every linear transformation, the zero vectors maps into zero vector, and the two properties are combined over here. If of a v plus b w, v and w belongs to the vector space V, this is equal to alpha a into f of v plus b into f of w. And if we generalize this property, and we say that there are not only two scalar a and b, there are many scalar ai, for example a1, a2, a3, a4, many different scalars belonging to the set of K, and many different vectors v1, v2, v3 belong to V. Then we generalize this property like f of alpha v1 plus f of a1 v1 plus a2 v2 plus up to am vm. We can generalize it like this. This is how we generalize the property of the two conditions of the basic definition of the linear transformation. And this remarks say that they are rephrasing this definition, and they have written this equation over here, and they say that by some authors this definition, this equation is used as an alternative definition of the linear transformation. So we have some remarks and some important examples over here that we will study on our line lecture. So until that, thank you so much. Allah Hafiz.